the Sustainability Management Master's Program, you're answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. But at the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
The Stevens Institute of Technology is proud to present the Hugo New Corporation Sustainability Seminar Series, co-sponsored by Geocentric Consultants, H2M Architect Engineers, Brown & Codwell, and BEM Systems.
All right. Hello, everyone. Thanks for joining today. Happy Art Day to you all. This is the final seminar of a very successful spring sustainability seminar series. We had 11 outstanding speakers this semester who talked about a wide range of projects in the sustainability space. I would like to thank them all, and to our sponsors, Hugo Corporation, BEM Systems, Brown & Caldwell, H2M Architects and Engineers, and last but not least, Geocentric Consultants. I would also like to thank you guys for being such a wonderful audience. When COVID-19 happened and we had to switch from on-campus to online mode of instruction literally overnight, I thought we would face some major problems in course delivery. We did not, and you guys are the main reason behind that, why we did not. Thank you for being so cooperative. Now, it's my great pleasure to introduce today's speaker, Lynn McGuire. Lynn is a senior principal in the San Francisco Bay Area with Geocentric Consultants, who, as I mentioned, are one of our sponsors. Thank you, George Hollerbach, if you're online. Lynn has over 30 years of environmental consulting experience to energy and industrial clients. At Geocentric, she leads the energy transition team, harnessing the firm's capabilities in environmental, natural resources, and infrastructure expertise for application to energy transition and sustainability solutions. She has taught courses in air pollution control systems and strategies and guest lectures on renewable energy for the University of California, Berkeley and Davis Extension programs. She has a BS in chemical engineering from UC Davis and an MS in chemical engineering from the University of Texas at Austin. It's all yours, Lynn.
Well, thank you so much, Dibs, sorry. I want to thank everybody for jumping online and spending yet another hour of your day online. I know we all might be experiencing a little bit of screen fatigue these days with this remote work that we're doing, but I am very honored to be the wrap-up guest speaker for the seminar series today. And I'm really disappointed that I couldn't be there in person, as I was looking forward to coming out to the East Coast. As Dibs said, I am from the San Francisco Bay Area offices of Geocentric Consultants, work out of Oakland and Walnut Creek, California. Geocentric has a staff of about 1,500 engineers, scientists, and related technical and project support in about 80 offices, mostly in the US and Canada. Dibs, you mentioned where I got my degrees from, but I also wanted to mention that I know some very sharp engineers who have degrees from Stevens Institute. My degree is in chemical engineering, and I decided to apply that to a 35-year career as an environmental consultant. And I've led a large practice in air quality and climate change services in the Western US for over 10 years. And my client base is largely industrial and focused on energy and power generation, manufacturing. And so this presentation, how industrial, let me go to the first slide here. There we go. How industrial businesses are charting a course to carbon reduction goals, brings together trends and information from my experience working with industrial businesses and items of interest that I have been following and learning from the trends and information that have been available recently in this space. Okay, so this is a high-level overview, and we're going to cover a lot of ground. I hope you find some things relevant and useful for your work and your studies in sustainability. Today, we'll touch on some of the drivers that there are for setting carbon reduction goals. We'll explain the importance of carbon emission accounting for scope 1, 2, and 3 greenhouse gas emissions in a carbon reduction strategy. And we'll discuss some important considerations in developing a greenhouse gas reduction strategy. We'll cover some of the most effective types of carbon reduction opportunities, including energy efficiency improvements, electricity supply and generation with renewable energy, fuel switching, efficient use and recycle of materials in their procurement, carbon capture and storage, and investment in carbon sequestration or natural resource solutions. We'll include examples of how these approaches have benefited businesses and the reputations of energy consumers, producers, and distributors as well. Well, I don't have to tell any of you that we are experiencing a time of change. In the last several years, there have been extreme weather events, and you've experienced them on the East Coast, and I've experienced the threat of wildfires and electricity interruptions in my own neighborhood. These events have caused businesses, consumers, producers, and the general public to consider how we conduct our daily activities to minimize disruption and become more resilient. And the current pandemic is teaching everybody lessons. Some of those lessons are relevant to climate change too. Both are issues of global significance, indifferent to geography, but may affect certain populations more than others. They call for changes and solutions based on our best scientific approaches that we hope will flatten the curve and prevent otherwise predicted devastating consequences. They're also stirring not only actions at the state and local level, but call for national and international efforts, as well as that of businesses, but also individual behavioral change. So it's a personal challenge. We expect that the COVID-19 experience will legitimize the concern for these threats and what can be done to prepare for and prevent the risks. There are a lot of differences, of course. The pandemic risk is sudden and temporal, causing widespread reaction and leaving things different than before. Climate risk is gradual. So up until now, you might compare it like the analogy of the frog that gets boiled in a pot of water as you slowly increase the temperature and doesn't necessarily react as immediately. But this temporal disruption is giving us a unique look at what the environmental impacts are of our business as usual. The air quality monitors here in California have recorded a few weeks of unusually clean air measurements. And as we recover, we may question how much we return to the business as usual. It may be a new business as usual. Many of the policies related to climate change in the US are adopted at the local city, county, and state level, and include a variety of low carbon technology incentives, greenhouse gas reduction programs, renewable portfolio standard mandates, energy efficiency targets, low carbon fuel standards, and even carbon neutrality goals. It's a unique time and one posing business risk, but also opportunity and innovation. So how do businesses identify the risks and opportunities? Each are on a journey and navigating this as best they can. However, investors like Vanguard, BlackRock, and State Street are aware of the challenges and have demanded more transparency about climate risks in financial disclosures, both around the changes happening around prevention of that are the transition risks and the changes to adapt to the consequences or the physical risks. And as a result, companies are now being held to emerging climate risk standards by investors. The TCFD is a global group with members that include banks, insurance, and asset managers, pension funds, large companies, accounting and consulting firms, selected by the Financial Stability Board, charged to develop a voluntary framework that businesses could follow in disclosing their climate-related risks. Their final recommendations were reported in June of 2017. So that's been about 3 years. And since that time, last year, over 1,100 companies have used the framework. That's 78% of the world's largest companies disclosing climate-related information aligned with at least one of the TCFD recommendations. The recommendations which address climate-related risks and opportunities are made around 4 core elements: that of governments, the business strategy, processes to identify and manage climate risks, and the metrics and targets that are set in alignment with that. As businesses disclose the transition risks, many are tracking metrics, setting targets and goals, and considering carbon reduction strategies, often as part of a corporate sustainability ESG planning, or to manage risk, improve the carbon footprint, and capitalize on opportunities. Many of the metrics involve energy and fuel consumption and greenhouse gas emissions. Industrial businesses in the US make up a substantial share of the greenhouse gas inventory and are responsible for providing goods and services and economic vitality and jobs in a clean, safe manner that align with the laws and regulations within the jurisdictions and communities where they operate. In the US, the 3 largest contributors to the overall greenhouse gas inventory are the transportation sector at 29%, the generation of electricity at 28%, and the industrial sector at 22%. But the industrial sector plays a key role as it also influences the transportation and electricity sectors indirectly as a consumer and a producer. The challenges for industrial businesses are many. Changes to business practices, processes, equipment, sources, supplies, fuel, energy use, emissions, and waste recovery all have an effect on carbon reduction efforts and are driven by multiple objectives. I've listed a number of those here on this slide: sustainability program goals, low carbon regulations and mandates from local jurisdictions, and supply chain mandates. Those that you sell your products to are starting to set standards for your product. And that's a driver that's emerging. Cost savings and investment and incentive programs, certainly, and scheduling of asset retirements, and prioritization of continuous improvements. Things around your reputation in the market, and of course, risk reduction. To gain an understanding of their relative position, risks, and opportunities to inform a carbon strategy, businesses must, at a minimum, have a clear picture of their current carbon emissions, including where they are located, how they define their operational boundaries, and what the most significant sources are. Companies that report their emissions under a mandatory program or framework will report on their direct Scope 1 and indirect Scope 2 emissions, while greenhouse gas reporting programs have very specific accounting requirements, Standard practice follows the principles in the Greenhouse Gas Protocol, a global standard supported by the World Resources Institute and the World Business Council for Sustainable Development. Scope 1 emissions are the direct greenhouse gas emissions from sources owned or controlled by the company, such as process emissions or combustion emissions from boilers, engines, or vehicles. Scope 2 emissions are indirect emissions from sources not owned by the company and occur due to the demand for the company's consumption of purchased electricity, heat, steam, or cooling. Some companies choose to include the Scope 3 emissions in their corporate inventories. Scope 3 emissions are the other indirect emissions that occur within the company's supply chain and provide a more complete picture of a carbon footprint. Such emissions would include greenhouse gas from the production of purchased materials, transport of purchased materials, end use of the product, for example, a fuel, ultimate waste disposal or material reuse, or sources outside the company's control, such as aircraft emissions from employee travel. Some factors to consider in whether to account for Scope 3 emissions in your inventory might be how available and reliable the data is from those emissions sources, your supply chain relationships, and the degree of responsibility or accountability or influence you desire. Okay. A company's greenhouse gas inventory will both inform and be influenced by the kind of carbon reduction strategy and targets it chooses to set. Companies set targets aligned with their sustainability program goals and the policies of the relevant countries and local jurisdictions they operate in. They also benchmark themselves against competitors, suppliers, and customers, liking to kind of stay up with what the other folks are doing. They also can elect to set science-based targets that are aligned with the level of decarbonization required to keep global temperature increase to below 2 degrees Celsius or 1.5 degrees Celsius compared to pre-industrial temperatures. An example given in the Greenhouse Gas Protocol, Procter & Gamble Company set very near-term science-based targets for this year, 2020, to achieve 30% reductions in greenhouse gas from a 2010 baseline year, and included other sustainability measures across its value chain, such as doubling the use of post-consumer plastic packaging, supporting zero deforestation in palm oil supply chain, and innovating its washing detergent designed to increase effectiveness of cold water washes to allow consumer energy reduction. Clearly, they have included Scope 3 emissions in their planning efforts for carbon reduction goals. Some companies have even chosen a goal of achieving carbon neutrality or net zero carbon emissions. In fact, I think we just saw that Shell Oil Company chose to do that by a certain year. You can appreciate the challenge this may present in balancing Scope 1, 2, and 3 emissions to a net zero, and the degree of influence on energy providers and material suppliers and resources a company must have in order to achieve a goal like that. Now let's talk about the carbon reduction options. The most obvious and the most cost-effective means to decarbonize industrial operations is to find ways to do more with less. With less fuel, that impacts Scope 1 emissions, and less electricity, which impacts your Scope 2. But energy efficiency has the potential to reduce both. Because energy efficiency is not a new concept, it is perhaps not as exciting or sexy or capable of drawing attention as other strategies. And identifying energy efficiency improvements at industrial facilities can sometimes be met with a belief that all good or cost-effective solutions have already been implemented. But taking a second look at ideas that were maybe not as economic in the past can result in identifying additional or new improvements to invest in. This is often quite true, particularly given changes to processes over time, advances in technology, lower cost energy pricing, and new alternatives. In circumstances where energy is cheap, like low-cost natural gas, being more efficient may not be a priority until you factor in what it can do to your carbon footprint. Most companies can reduce the overall energy use and associated greenhouse gas emission potential of their operations by at least 10% or better with relatively small investments that lead to cost savings, and up to 35% by making substantially larger investments that might also lead to cost savings. If there's such a good idea, why don't we commit to doing these projects? Well, it's a lot easier said than done. Many companies maintain a list of good energy efficiency projects that await the right timing and budget cycle to be executed. Planning and scheduling these projects is often done incrementally, like my list of energy saving projects for my home here. A new energy efficient furnace went in when the original one finally was at end of life, and no sooner. The solar panels just had to wait until a new roof was installed in my house, and data collected on other changes that affected my home energy demand. Well, maybe now it's time. And incentives and access to capital really help here. One way to visualize the attractiveness of energy efficiency projects in creating a greenhouse gas reduction strategy is to create a marginal abatement cost curve, or a MAC, for the suite of greenhouse gas reduction opportunities. The opportunities can be identified through surveying experts familiar with the facility energy systems or by conducting an energy audit. In a MAC curve, each bar represents a different opportunity to reduce emissions. The width of each bar represents the annual emissions reduction potential of the opportunity compared to business as usual. And the height of each bar represents the average net cost of reducing 1 ton of CO2 equivalent through that activity each year. Capital costs are included and annualized into these cost figures. The opportunities below the horizontal axis are cost savings. The opportunities above the horizontal axis reduce carbon but have a net cost. This is an example shown here from the California Air Resources Board proposed rulemaking for its cap and trade program, and depicts energy efficiency options for a typical oil refinery. Optimizing and maintaining heat and steam systems are some of the cost-saving opportunities, while replacing large equipment and assets like boilers and heaters require big investment. And those are above the horizontal axis. Some typical energy efficiency measures for industry might include optimizing steam systems, like we mentioned, and fixing leaks, balancing, replacing motor drives with high efficiency or variable speed drives, optimizing pumping and compressed air systems, waste heat recovery, using combined cycle rather than simple cycle turbine equipment, upgrading heating and cooling systems, insulation improvements, building energy design and lighting improvements like LED lighting, and investing in instrumentation and controls. Other measures could involve programmatic approaches, such as implementing voluntary energy management systems. I think most people are familiar with the Energy Star program. We see the logos on our appliances. It was established by the US EPA in 1992 under authority of the Clean Air Act, and it sets performance-based criteria for energy efficiency and oversees third-party certification of products. EPA expanded the program to industrial energy efficiency in the year 2000. There are now 790 industrial companies that partner with EPA under the Energy Star Industrial Energy Management Program to reduce greenhouse gas and improve energy efficiency at their facilities. This program provides tools for building a program, benchmarking, sharing best practices within sectors like their energy guides, and tracking performance against indicators, engagement and communication, as well as recognition and awards. Since 2011, The ISO 5001 standard came about and gives organizations a framework for an energy management system based on the classic plan, do, check, act process of continual improvement. It starts with an energy policy, fixing targets, gathering data for decision making, measuring results, and reviewing effectiveness and continually improving. And another recently developed programmatic framework to engage for an energy strategy in alignment with sustainability goals follows the guidelines that are established by the World Business Council for Sustainable Business Development as a part of an integrated energy management strategy. The solutions and guidance offered for reducing energy and fuel consumption through these energy efficiency measures focus on 3 areas: engaging with your workforce and value chain partners to improve energy efficiency, using smart controls to improve energy and fuel efficiency, and upgrading and replacing equipment and assets. The guidelines provide examples and building blocks for success for businesses to use in creating their own approach and solutions for energy efficiency. Of course, changing the source of electricity itself to renewable sources is another way the industrial sector can achieve significant reductions in reported Scope 2 greenhouse gas emissions. Facilities can install their own on-site rooftop solar PV panels or ground solar arrays or small wind turbines. Self-generated renewables are a distributed energy resource and are located behind the meter with the utility. All electricity generated is carbon-free and can substantially reduce the amount that is provided by the grid and the associated greenhouse gas emissions with that. Companies also contract for off-site generated renewable sources by purchasing not only the power, but also renewable energy certificates, or RECs, which are market-based instruments that represent 1 megawatt of electricity generated and delivered to the grid from a renewable energy source. RECs convey the property rights to the environmental and social and other non-power attributes like your zero carbon credit of renewable electricity. Electricity and RECs are distinct products though, and can be sold separately as unbundled products or together. Physical power purchase agreements, PPAs, were the most common form of transaction in the early years of the corporate renewable energy market. They are contracts for renewable power where the corporate buyer is purchasing the electricity generated and the RECs at a certain renewable energy project. The electricity produced needs to be physically used by the buyer, so you need to align the project size of the energy project with your facility load, which places kind of an upper limit on the greenhouse gas benefit. Often they require the generating facility and the company's operations to be located within the same grid region and may need to be in deregulated retail states. So virtual PPAs, as they're called, have become the fastest growing transaction structure today for corporate buyers because the buyer does not own and is not responsible for the physical electrons generated by the project, but they do receive the RECs from entering into these contracts. Instead of routing renewable power directly to the buyer's facility, the generation facility sells their renewable power directly to the grid and receives the open market price with a true-up on the price with the project developer. They are easily scalable and enable buyers to satisfy large portions of their sustainability goals with relatively small number of deals, which is nice for loads that you might have across regions. They can have contract pricing advantages and require less market awareness. Two of the most common types of these kinds of contracts are wind and solar contracts. The majority of commercial scale renewable energy project PPAs to date have been wind contracts. Excuse me. Okay. And in 2018, wind energy contributed 6.5% of the nation's electricity supply, with newer projects proposed that are pairing with energy storage. The price of wind energy dropped from around 7 cents per kilowatt hour for PPAs executed in 2009 to a 2019 average price of below 2 cents per kilowatt hour, comparing favorably to future costs of gas-fired generation. Corporate solar PV procurement is expected to overtake wind as the renewable source of choice for corporate buyers in the next 5 years or so, due to forecasted favorable solar pricing and the step down of federal tax credits for wind energy. We can share a few examples of recently reported that are recently reported by others of green power action by corporate buyers. First, one from the oil and gas industry finding uses for green power PPAs to produce oil. In 2018, ExxonMobil signed 2 PPAs of 250 megawatts each to purchase both wind and solar power in West Texas to power their expanding operations in the Permian Basin. The electricity is generated in essentially the same region where the oil fields are located. Next, an example from power generation industry highlighting competitive costing of renewables plus storage. Xcel Energy has a goal to reduce carbon emissions by 60% by 2030. And to accomplish this, the utility planned to shutter coal-fired capacity at a generating station and replace it with lower carbon alternatives. Xcel recently requested proposals for natural gas and wind or solar plus storage. The responses resulted in an unprecedented low cost for renewable energy and storage. The median price bid for wind plus storage projects in the solicitation was $21 per megawatt hour, and the median bid price for solar plus storage was $36 per megawatt hour. Previously, the lowest known bid for similar solar resources was $45 per megawatt hour in Arizona, a full $9 per megawatt hour cheaper than the lowest contract amount the prior year. And importantly, the computer data industry with vastly growing power scope 2 consumption needs. Google is an example of a corporate leader in carbon-free energy procurement across the US and the world. They've invested over $2.5 billion in at least 34 PPA agreements totaling more than 3.7 gigawatts of renewable energy, allowing them to operate on 100% renewable energy. They've been carbon neutral for 12 years, and to date they have purchased nearly 26 million megawatt hours of renewable energy through PPAs, VPPAs, and other purchasing tools. In 2018, their gross scope 1 and 2 greenhouse gas emissions were 4.4 million metric tons of carbon dioxide equivalent, but renewable energy purchases reduced their net greenhouse gas emissions by 3.7 million tons. Lastly, a traditional manufacturing industry and how a VPPA that almost didn't happen results in a large greenhouse gas footprint reduction is the manufacturer Cummins, the large engine and generator manufacturer headquartered in Indiana. They had a 2016 goal of 32% reduction in energy use and greenhouse gas intensity by 2020. As part of the plan, Cummins chose a VPPA for wind energy project being constructed near its load center in Indiana. The Indiana Meadow Lake project took advantage of a practice known as REC swapping between 2 adjacent markets to improve the economic outlook of the VPPA, and it was signed. The electricity generated is planned to be equal to the amount of Cummins usage in the state of Indiana, which is about 25% of its total company greenhouse gas footprint. Now we'll switch gears and talk about fuel switching. Substitution of carbon-intensive fuels in manufacturing processes can be very difficult in highly integrated manufacturing processes, especially to meet high thermal and energy process needs. Many large manufacturers in industrial sector collaboratives like steel, cement, chemicals, petroleum, and petrochemicals are weighing their options, though. Fuel switching is a significant step and can result in significant greenhouse gas reductions when moving to even incrementally less carbon-intensive alternatives. It is important, however, to realize that every fuel has its own carbon footprint, including not only the carbon released when it's burned, which is the red part of the bars shown in this chart, but the carbon that it took to produce and transport the fuel. Thus, low carbon and conventional fuels are often characterized through a life cycle assessment to determine a unique carbon intensity. The figure shows a comparison of carbon intensities in grams of CO2e equivalent per megajoule for conventional fuels, and you can see the general advantage of moving from something like coke or coal to natural gas, LPG. This next slide shows how not all natural gas is created equal, considering where it comes from. Again, it's important to understand the carbon intensity value for the fuel, including all the processing and shipping components of its footprint to make clear choices that benefit greenhouse gas reduction decisions. This example compares shipments of US-based LNG, or liquefied natural gas, to the European market. Compared to LNG from Algeria or natural gas from Russia to replace regional European coal greenhouse gas emissions. Depending on the origin of the natural gas, how it was extracted, compressed, and transported, the greenhouse gas emissions are quite different. And for the shorter 20-year scenario for methane global warming potential, one type of natural gas is almost as carbon intensive as the coal it would replace. There are, of course, alternatives to non-fossil based fuels to consider. Biomass is organic material from plants and animals that is considered a renewable energy source. Biomass stores energy, as in plants through photosynthesis, and burning biomass releases the energy as heat. Ethanol is a fuel that is being used widely as a low carbon fuel and blended with gasoline in the US to lower carbon intensity of gasoline and reduce emissions. Just as we saw with natural gas, though, not all ethanol is created equal. This shows some information on energy use, providing an example of how using biomass as a fuel in ethanol production can create a very low carbon ethanol biofuel. Almost half of the life cycle energy contribution for Brazilian sugarcane ethanol is in the ethanol production step, which uses heat energy. Most of the remaining life cycle energy is in the ethanol fuel itself and is released when it is combusted as a fuel. By supplying the heat energy for production by using a renewable biomass fuel, the waste bagasse from the sugarcane itself, the production step contributes almost no greenhouse gas emissions to the overall carbon intensity of the fuel. There are many alternatives for non-fossil based fuels being used to lower carbon emissions. Biomass and biogas, often referred to as renewable natural gas, are most commonly waste-derived fuels from wood waste, agricultural waste, landfill gas, municipal solid waste, or at least the organic portion of it. So some of the best sources of renewable fuels are from some form of waste. Waste is becoming the fuel of the future. Hydrogen is an interesting alternative that is receiving attention, but not all hydrogen is created equal either. Large quantities of traditional hydrogen are produced very efficiently and economically by steam methane reforming, a process that is unfortunately generating very large quantities of CO2 as a byproduct. This is becoming known as gray hydrogen. By contrast, green hydrogen is produced in much lower quantities by the electrolysis of water, a very energy-intensive process, but can be performed using electricity from a renewable energy source, for example, wind or solar. But it can be very, very expensive. Making green hydrogen from excess intermittent solar or wind resources that are curtailed or wasted at off-peak times is one way to store the energy and recover its value, and from perhaps maybe some energy sources that may be otherwise a waste. So this is getting attention. To produce large quantities of renewable hydrogen, however, most cost effectively, It may be by traditional steam methane reforming, but by capturing the CO2 emissions and sequestering them. That is known as blue hydrogen. These options offer promise in providing deep decarbonization benefits with attractive niche applications to turn waste into fuels or waste energy into gas in the form of power to gas or storage, and make renewable energy from renewable fuel, like gas to power applications. And electrification of processes to achieve greenhouse gas reduction, I might remind everyone, only makes sense if the electricity supply is renewable itself and affordable and reliable. The lifetime of an industrial facility is often on the order of 50 years or more, so making significant changes to accommodate a new feedstock or fuel type that requires fundamental redesign could be a very slow process. Additionally, the current choice of fuel and design is influenced by availability and economics. For many manufacturers, production using low carbon fuels, if even feasible and available in the quantity and location that's needed, and reliable, will likely come at a higher cost, at least in the interim. There are many examples of how industrial businesses are looking at their entire manufacturing process, including procurement of materials up the value chain from suppliers, like we mentioned in the Scope 3 emissions inventories. This involves making changes to feedstock or materials that directly reduce the plant's Scope 1 greenhouse gas emissions and the product's carbon intensity and developing ways to reduce waste. Tackling the problem of the carbon emissions from cement manufacturing is an example of a very complex issue requiring consideration of multiple approaches, such as the materials used and the manufacturing process itself. Since cement manufacturing alone is reported by many to account for about 7% of all global carbon emissions and is an essential in infrastructure and buildings, international collaborative efforts are underway to develop decarbonization solutions. Everything from energy efficiency to using alternative fuels to carbon capture and storage to new formulations, reducing the clinker content, and alternative binding materials are being attempted. Manufacturing cement requires very high temperatures, which requires a large amount of fuel, but it is the decomposition of the limestone in the formation of the clinker that generates at least half or more of the CO2 emissions from cement manufacturing. Thus, cement operations are attempting to use recycled materials, steel slag, fly ash, and clays to replace all or some of the clinker. Because the transition of industrial sources to low carbon processes will take time and the desire exists to hasten decarbonization, both companies and jurisdictions that ascribe to carbon neutrality goals are coming around to supporting carbon capture or carbon removal strategies, resulting in negative emissions. Carbon neutral doesn't mean zero carbon emissions. It means the amount emitted is balanced with a reduction of the same amount to achieve a net zero. Negative emissions, then, are getting attention in carbon reduction strategies, especially if the strategy is to achieve net zero. We talked already about how carbon can be captured from waste and converted to fuel. Waste can also be converted to energy, as we mentioned too. Municipal solid waste to energy and landfill gas to energy are examples of carbon neutral or carbon negative approaches. Biomass conversion to electricity or fuel and storing the CO2 is being considered as a way to pull CO2 from the atmosphere and sequester it. We talked already, other ways that we haven't talked about to use CO2 captured from processes might be like from fermentation and using it then in beverage production. And CO2 is also now being captured and used as an additive in cement manufacture. There are also developers of what are called direct air capture systems. These are big fans that capture ambient air and filter it and separate the CO2 from the air for sequestration or for use. In the case of methane emissions, which has a high global warming potential, 25 times higher than CO2, carbon capture by leak prevention and reduction has been addressed through toughening regulatory standards for leak detection and repair, or LDAR, for methane in many industries, especially in oil and gas production and gas distribution systems. However, there are still industrial waste and biogenic sources of methane that are large contributors to greenhouse gas emissions on a regional and a global scale. For example, the largest contribution of methane emissions in California is from landfills. This map is showing Southern and Central California sources of methane found in a recent measurement study conducted by NASA's Jet Propulsion Laboratory that flew over the state of California with remote sensing infrared imaging equipment. Blue dots represent waste sources, generally the landfills. Yellow blocks are the energy sites, oil and gas production, that contribute about 26% of the methane emissions. And the green dots are agricultural or biogenic sources that contribute about 26%. All of this leaking methane gas is also considered a renewable energy resource if it is captured and used. So we talked about capturing CO2 and a few types of uses, but let's talk about storage now, or sequestration. The most mature storage technology is geologic storage. In fact, CO2 has been injected into geologic formations for many years for enhanced oil recovery, a means to extend the production life of oil fields. This technique has been practiced since the 1970s in the US. The CO2 storage had originally been regarded as incidental, and the technique was economical because of the significant cost of capturing, transporting, and storing the CO2 is offset by the value of incrementally more produced oil. Such conditions exist in the Permian Basin, where over 60 million tons per year of CO2 is used for enhanced oil recovery. More recently, incentives such as the 45Q federal tax credit and policies such as California's low carbon fuel standard and cap and trade program, which monetize carbon, are now establishing accounting systems and providing rewards for the climate benefits of putting CO2 under the ground. Reservoir characteristics, location, CO2 source and transport through pipelines, funding, collateral benefits, and a means to account for and credit the CO2 reduction, as well as many other factors, must all align for implementation of carbon capture and storage to be economical and successful. An example of large-scale carbon capture and storage for enhanced oil recovery is a project being developed for California Resources Corp, who partnered with EPRI, the Electric Power Research Institute, and Fluor to design a permit by 2030, California's first carbon capture and storage project, and the largest in the US at its Elk Hills oil field. The project will capture and store 1.5 million metric tons of CO2 emissions from its nearby Elk Hills power plant. Studies have identified suitable storage zones in California's Central Valley alone, comprising a minimum of 17 billion tons of CO2 storage capacity, though much additional evaluation of geologic, seismic conditions, as well as man-made penetrations must be investigated carefully to confirm storage suitability. Other critical considerations for additional future carbon capture and storage projects are the expansion of pipeline infrastructure to transport CO2 from large sources and to the fields, and long-term monitoring of these projects to prevent or quantify any potential leakage. Since carbon sequestration takes place every day in the natural environment, the business community is also taking cues from natural processes to develop approaches. This includes investing in solutions and programs aimed at natural processes and land management, land use management. that improve carbon sequestration by maintaining vegetation, trees, soil, and wetlands. Projects with goals of restoring and protecting forests, soil, and wetlands needing funding are finding corporate partners. Some of these solutions are proving to be more economical on a dollar per ton of carbon basis than other sequestration methods. These projects have very, very attractive co-benefits to air and water quality, ecosystems, soil health, and resilience to climate change, and wildfire protection. European oil and natural gas companies are leading the way to incorporating these kinds of plans into their company carbon strategies. In 2019, Eni, a major Italian energy company, announced its plan to emission developing and funding forestry projects in Africa through the UNFCCC RED Plus program. And Shell announced plans to invest $300 million over 3 years in natural ecosystem-based projects, initially focused on reforestation projects in Europe. Additionally, while tree planting and forest management are important to managing the global carbon balance, soil management to prevent depletion of soil organic carbon is getting attention as well. Some report that the Earth's soils contain more than 3 times the carbon than is stored in the atmosphere, and 4 times more than the amount in all living plants and animals. But programs to assess the potential for carbon sequestering land management and farming practices are still in the research stage, and protocols for accounting are in the pilot stage. While soil carbon sequestration may have enormous potential and co-benefits, some of the challenges are in quantifying the reductions, accounting for the effectiveness over time, and demonstrating the permanence of the reductions and uncertainties, such as resilience to weather events.
Sorry to interrupt. You'll have last 5 minutes here.
Yeah, and good timing, Samir. This is the last slide. And it's the takeaways from this talk. The takeaways are, and I hope that you remember them all from the talk, an increasing number of companies are starting to set their carbon reduction targets, and a big increase has happened in the last 3 years. Energy efficiency solutions can achieve significant greenhouse gas reductions and are often cost-effective. Renewable electricity options and electrification are becoming economical ways to cut greenhouse gas emissions. Fuel switching can achieve very large reductions, however, require attention to life cycle impacts. And alternatives need to be feasible, available, reliable, and affordable. Carbon capture and sequestration is now getting a lot more attention, and investing to enhance natural carbon sequestration is a strategy used to achieve carbon neutrality with important co-benefits. And that's really it. We covered a lot of information, and I again want to thank you for your attention. I also want to acknowledge 2 other members of my team, Hong Jin in Houston, Texas, and Barb Neary in Denver, Colorado, who work with me on our energy transition projects and contributed to this information that was presented. I hope that this has sparked some ideas for you and maybe a few questions.